All right, let's get into it. Today, we are tackling one of the biggest wonders of biology, how you see. It feels so simple, right? You just open your eyes. But the journey that a single particle of light takes to become a thought, an image, a memory in your head, well, that's an incredible story. I mean, really, stop and think about that for a second. How does pure energy bouncing off stuff in the world turn into the rich, colorful, three-dimensional experience you're having right now? That's the puzzle we are going to piece together today. And this is going to be our roadmap. Now, it looks a little intimidating, I know, but don't worry, we're going to take it one step at a time. We're going to follow a visual signal from the retina that's in the eye through a critical little relay station and then deep into the brain's visual cortex. So let's start where the light first hits the eye. Okay, so our journey starts right at the back of your eye in a layer of tissue called the retina. Now, this is not just some simple digital camera sensor. Oh no. The retina is actually a super sophisticated piece of your brain that's located in your eyeball, and it does a ton of processing before a signal even thinks about heading deeper into your head. Think about it like this. The cells that send messages out of the retina, they're called ganglion cells. They're not all the same. It's way more clever than that. They act like a team of specialist reporters. So instead of getting one boring, generic story, your brain gets multiple parallel reports, each one focusing on a totally different aspect of what you're looking at. So let's meet the reporting team. First up, you've got your Parvocellular cells. These guys are the vast majority, like 80% of the team, and they are the detail specialists. They've got tiny receptive fields, which is perfect for high-resolution vision, fine details, and color. Then you have the Magnocellular cells. About 10% of the team, these are your motion detectors, big receptive fields, super sensitive to any kind of change or movement. And there's a third kind of mysterious group called Koniocellular cells. We'll come back to them because they have a really cool specific job to do with color. Okay, so all these different reports leave the eye and head for their first big stop in the brain. It's a place called the lateral geniculate nucleus, or just LGN for short. And this place is not just a passive pit stop, it is a critically important sorting hub. Yeah, the best way to imagine the LGN is like a massive, super efficient mail sorting office. It grabs all the incoming signals from both of your eyes and meticulously sorts them. It's like, okay, your detail signal, you go here. Your emotion signal, you go over there. You're from the left eye, you're from the right eye. It gets everything perfectly organized before shipping it off to the main headquarters, the cortex. And check this out. This is what that sorting office actually looks like up close. The LGN isn't just a random lump of cells. It's organized into these 6 beautiful, distinct layers. You can literally see the organization. This isn't just random biology. This is designed with a purpose. So let's look at how the mail gets sorted. The top 4 layers, that's 3, 4, 5, and 6, they handle the parvocellular information. That's all your high-res detail and color. The bottom 2 layers, 1 and 2, they're for the magnocellular stream, the motion stuff. And here's the really clever part. Each layer only listens to one eye. So the info from your left and right eyes is kept totally separate, but it's all lined up perfectly, creating these 2 identical stacked maps of the world. All right, from our sorting hub, these perfectly organized signals travel to their grand destination, the primary visual cortex, what we call V1. Now, this is where the real work of seeing begins. This is where your brain starts to deconstruct the world. I like to call V1 the feature factory, because it doesn't see a face or a car. Not yet. What it sees are the absolute most basic components. It sees tiny little lines, edges at specific angles, little patches of color, and bits of motion. It takes the whole picture and shatters it into its fundamental building blocks. And just like the LGN, V1 is also built in layers. You can see here how those sorted signals from the LGN plug right into specific layers in V1. See that big middle layer, layer 4? The parvocellular stream, the detail one, and the magnocellular stream, the motion one, arrive in different parts of that layer. That separation we saw in the LGN, the brain makes sure to maintain it because it's absolutely crucial for what comes next. And here's where things get really, really wild. V1 isn't just one picture of the world. It's more like a stack of translucent maps, all laid on top of each other. And each map is analyzing a completely different feature of the very same point in space. It's pretty mind-bending. So, map number 1 is called retinopathy. That's a fancy way of saying that the map of the world is preserved. Things that are next to each other out in the world are processed by brain cells that are next to each other in V1. But here's the twist. Everything you see in your left visual field gets processed in the right half of your brain, and everything in your upper field of view gets processed in the lower part of V1. Kind of weird, right? Map number 2, ocular dominance. Remember how the LGN kept the signals from each eye separate? V1 does too. It actually organizes its cells into these alternating stripes like a zebra pattern of left eye cells and right eye cells. And by comparing the tiny differences in the signals from these adjacent stripes, your brain starts to calculate depth. This is the very beginning of how you see the world in glorious 3D. Now this is my favorite map. This is the orientation map. See, neurons in V1 are incredibly picky. One cell might only fire when it sees a vertical line, and another only for a line tilted at exactly 22 degrees. And what this incredible image shows is that cells that like the same angle all cluster together. They form these absolutely beautiful patterns called pinwheels. At the center of every one of those pinwheels, you can find a cell for every single possible angle. It's amazing. And our last map is for color. Just sprinkled throughout all those other maps are these little spots, these clusters of cells that scientists call blobs. And these blobs get their own special delivery of information from that Koniocellular pathway we mentioned earlier. Their entire job is to process color. So think about it. For any single point in your vision, V1 is simultaneously analyzing its location, which eye saw it, all the angles of the lines there, and its color, all at once. Okay, so V1 has completely deconstructed the world into a storm of lines, colors, and motion. But that's not what we experience, is it? We see whole objects. So how does the brain put Humpty Dumpty back together again? Well, in a really strange and fascinating way. It splits the information from V1 and sends it down two completely separate highways. And this diagram just lays it all out for us. You can see the information leaving V1 at the back of the brain and splitting. One path, the ventral pathway, heads down towards your temporal lobe. We call this the what stream. Its job is to figure out what you're looking at. The other path, the dorsal pathway, goes up into the parietal lobe. This is the where stream. Its job is to figure out where the object is and how you can interact with it. This division of labor is just wild. The what pathway lets you look at a mug and say, that's a coffee mug. The where pathway calculates its exact position and shape so you can reach out and grab it. And get this, if you have damage to your what pathway, you might be able to reach out and grab the mug perfectly, but you'd have no idea what it is you're holding. Flip that, damage the where pathway, and you can say, oh, that's my coffee mug, but you'd be totally unable to guide your hand to pick it up. Your brain literally sees what an object is and where an object is in two completely different places. And as you go further down that what pathway, the brain cells get unbelievably specialized. Just look at this recording from a single neuron. See how it goes absolutely crazy with activity when it's shown a face? But then, when it sees a hand or a clock or just a random pattern, nothing. It's totally silent. This is your brain literally building the concept of a face from all those simple lines and shapes that V1 detected. Meanwhile, over in the where pathway, it's all about vision for action. You've got areas like MT and MST that are geniuses at calculating motion, figuring out if you're moving or if the world is moving. Then you've got other spots like VIP and LIP that are constantly updating a map of the space around you, guiding your hand when you reach for things. This whole pathway is what allows you to actually interact with your world. And that brings us to the biggest question of all. We followed the signal all the way from a photon of light to these separate brain areas, one that knows what an object is and another that knows where it is. But your experience of the world isn't fractured. It's seamless. You don't see a what over here and a where over there. You see a single unified thing. So if the brain takes the world apart in order to understand it, how, and more importantly where, does it put it all back together again for you? That is one of the deepest mysteries left in all of science, and something to think about the next time you just, look at something.